Action. So guys, this day used to have a whole lot more meaning years and years ago because all of Dr. Hess's kids from over at BYU came through Orem High and they all took AP chemistry from me, and we used to have a similar experience to Super Nate talking about Hess's Law, but those days are gone. And so No. Just a guy named Dr. Hess. He's lovely. All of his kids went here. Anyway, it has nothing to do with us. What's Hess's Law? It's this. Write it down. So guys, Hess's Law, which I already alluded to last time, says this. If a reaction can be broken down into a series of steps, the sum of the enthalpy changes associated with the steps will equal the enthalpy change of the complete process, the complete change. I gave you the analogy last time in class that if you know how much gas it takes to get from here to Boise, and if you know how much gas it takes to get from Boise to Seattle, you know how much gas it takes to get from here to Seattle. Kind of makes sense, right? That if you can break a trip into steps, like going from here to Seattle and stopping in Boise, if you can break a journey into steps, if you know the energy associated with the steps, then you can figure out the energy that it takes to take the whole journey. You good with the concept? Okay. So guys, with the concept then, you need to understand that you're going to interact with this in two different ways. Now guys, to help you cleanly make the transition between these, you need to grab your equation sheets. So grab those now, have them at the ready, have them open to the thermoelectrochem section. And guys, as you're doing this, I don't know if you want to reference that flow chart that I gave you on Tuesday. You don't need to. But this is, and you don't need to write this down. This is the way this is going to play out. The logic behind Hess's Law, this idea of breaking processes down into steps, this can actually be addressed, and on the AP test, it could be addressed in one of two ways. Through a process of manipulation or through a process of calculation that we call heats of formation. And so guys, we are going to approach these in order. But the way that I'm going to do this is I'm going to explain to you the manipulation process first. Then, once you understand the manipulation process, I'm then going to teach you what heats of formation are. Then once you understand what a heat of formation is, we are going to do another manipulation process, which you will magically discover is actually a heat of formation process. And you're going to go, hey, that was neat. And you're going to find out that these are actually the same thing. It's just that the heat of formation process is a shortcut to making the manipulation less big and kind of complicated. So you'll see. But these things are very closely related. So you guys ready to go? First thing we're going to do is we are going to do Hess's Law by manipulation. Who could it be? I never win. J1. Thank you. I'll split it with you. Okay, so guys, this is the way this goes down. You see a problem on the test, you see a problem on what it looks like this. I would encourage you not to write this down, just trust me, I'll show you what you should write down. But what they will do is they will give you some information. they will give you a point of reference. And guys, that point of reference will actually be information about the steps. So think about it this way. They might give you how much gas it takes to get from here to Boise. Okay? Think about this. How much gas it takes to get from here to Boise. Then they might also give you how much gas it takes to get from Seattle to Boise. Can you still figure out how much gas it takes to get from Salt Lake to Seattle? How? How do you do it? Well, but wait, how does that work to add them up? Because you don't know how much gas it takes to get from Boise to Seattle. They told you to Seattle to Boise. But it's the same in the other direction, right? Guys, that's the whole idea of manipulation, is you've got to be able to flip these things around in your head, because sometimes instead of giving you Boise to Seattle, they give you to Seattle to Boise, and you've got to understand that it's the same just in the other direction. And by flipping those things around, eventually you can get them to all add up and give you the whole trip. Get the idea? Okay, that's actually a pretty good analogy. That just occurred to me. That was pretty good. All right. So, really, I've been doing this for 13 years. It seems very obvious. That just came to me. I'm learning as well. So, guys, this is the way they'll actually present it to you, and this is what you want to write down. This is this in equation form, in balanced equation form. So, the enthalpy of combustion of carbon to carbon dioxide, that's this, carbon to carbon dioxide, is negative 393.5 kilojoules. Okay, now this one you're not going to like, so I'm going to do it with you. Oh, you know what? Hold on. Bye-bye. No, you're okay. I just forgot to get my drawing tools. Okay, so guys, again, this is where we're at right now. We've got this. And hopefully you're okay with the idea that this is carbon, this is carbon dioxide, combustion involves oxygen, and there is our energy. Good? Okay, so now guys, let's see if we can turn this into a similarly balanced equation. So now it says the combustion of carbon monoxide, let me give myself a little more space. So we're going to have to balance this. So the combustion of carbon monoxide, so combustion involves oxygen, to carbon dioxide is sorry, I ran out of room, but we're okay. Is that? Just a second. You okay? It's what?
The second one. First it was what is this?
This is that.
Well, no,
So, carbon monoxide.
I was talking about the enthalpy changes.
Okay, hold on. So, carbon monoxide, carbon dioxide, combustion, and that's the energy. You okay?
I just saw on the first equation you just have kilojoules, like how do you have
Okay, are we good? Okay. Now, guys, here's the problem. This is not balanced. One carbon, one oxygen, well, 3 oxygens, 2 oxygens. Please do not write down what I'm about to do. 1 oxygen, 3 oxygens, 2 oxygens. We have an odd-even conflict, so what do? Double the odd number, which then places a 2 here, and now it's balanced, right? Here's the problem. We just made the entire statement invalid. Why? Because this is 2 moles, and this is per mole of carbon monoxide. So this number is no longer reflective of this balanced equation, because this is now written as 2 moles, but this is the energy for 1 mole. So I heard somebody say what we could do. It was someone over here. Double that number. But that's not what we're going to do. Here's what we're going to do. We're going to divide all of these by 2. And dividing all of those by 2, look at what we get. Carbon monoxide plus 1/2 mole of oxygen yields carbon dioxide. Guys, we are now giving ourselves the freedom to balance equations with fractions. The reason that we're doing that is because it is important for us, and this is kilojoules per mole of carbon monoxide, it is important for us to balance our equations so that we have 1 mole of the subject compound, in this case carbon monoxide. So guys, what we're going to do is rather than double or whatever these numbers, we are going to balance our equations with fractions so that there is always a 1 associated with the compound that we're tracking down the energy change for. You okay with the idea? Okay. I know it's new. That's the way we're going to handle this. That's the way chemists handle this. So these are now these equations balanced so that they are now representative and useful for us.
So are we going to balance equations with fractions just for Hess's law?
Just for thermochemistry. Yes, just for thermo. Okay, so now guys, watch what we're going to do. I'm going to rewrite these. Just humor me for a second, because I need these to be manipulatable. And I'm going to be loose with units. And then okay. So did I do that right? That looks good, right? Okay. So now, guys, this is where this is headed. When you're doing Hess's law by manipulation, frankly, they will just give this to you. On the test, I can show you examples off of old AP tests. They will give you a toolbox, if you will, of equations, thermochemical equations. They will give these to you. And it'll look just like this. They won't give it to you as words. They'll give it to you like this. And again, I've just rewritten them so that I have something that I can play with. Go away. Okay, so now this is the way the question will continue. It'll say something like this. Calculate the enthalpy of combustion of carbon to carbon monoxide. So this then is the big idea. Given these, calculate this. How much energy is involved in converting carbon to carbon monoxide? Guys, this is the way you handle the process. You ready? The first thing that we need is a balanced equation, and we are going to call this our subject equation. Okay? So we need to write a balanced equation for this. So guys, go do it. Write a balanced equation for that process. Absolutely. You're going to balance this with fractions. You're going to have to. So calculate the enthalpy of combustion of carbon to carbon monoxide. Because if you're not tuned in with what we're doing, we are writing the balanced equation for this process. I'll give you another second and then we'll talk about it. You okay? So it goes like this. Carbon this one's pretty easy to come back from. Okay, so carbon is being converted into carbon monoxide. Now guys, in order for that to happen, what's it doing? It is combusting. What is combustion? It is a reaction with oxygen. And now in order to make this balance, what do? We add a 1/2. You okay with that? Okay, so now guys, this is the big picture. This is the way this will play out on the test. Here are our given bits of information. Here is our subject reaction. And now guys, the way that this is going to play out is through the context of Hess's law. So the idea is this: if we can make these add up to this, then if we can add up the energy changes of these, it will then give us the energy change of this. Do you get the idea? So what's the tricky part? Making these add up to this. So how are we going to make these add up to this? By manipulating them. And what does it mean to manipulate? It means to flip them back and forth, and it means to multiply them by factors such that these magically turn into this. Do you understand the context of what we're doing? You're okay? All right. So guys, with that as a background, here's what I'm going to have to do. I'm going to clear this, make my screen white, go back here, and then guys, what I'm going to do is I'm then going to write down our subject reaction. But guys, what I think I'm just going to start completely over, because this is easier if it's higher, because I'm going to run off the screen. So give me just a second here and let me catch up. So what did the first reaction look like? Okay, so we've got I better stick with red because some of you are going to go, wait, it changed colors. Carbon plus oxygen yielded carbon dioxide. And what was the energy associated? This is the 393 point what? 5K. And I left off units. And then this one was, and it yielded CO2. And that was, am I okay? Okay, now guys, again, those are the reactions that we're going to manipulate. Now we need our subject reaction, and I'm going to skip down here, and that was, I believe, carbon plus 1/2 O2 yields carbon monoxide. Am I all caught up with you? Okay. So guys, given this is the stage, and this is largely what this will look like on the test, in order to figure out the delta H for this, what we've got to do is turn this into this. So how do you do it? Guys, here's the way to play this game. Again, what are we calling this reaction? Subject reaction. Start with your subject reaction, read left to right, and every time you run into a critter, find it up here and make sure it's in the right place and has the correct number of things. So the first thing we run into is carbon. Where is carbon up here? It's in the first reaction. So now we found carbon. Is it on the correct side? Yes. Are there the correct number of carbon atoms? Yes. So that didn't involve any manipulation. Now we find oxygen. And when we look up here for oxygen, guys, is the oxygen on the right side? It is. And is there the correct number of them? No. But here's the deal, guys. If you find a substance in more than one of the reactions that you're given in your toolbox, don't start getting weird. Leave it alone. It may work itself out. So again, the principle is, if you find something in more than one place up here, don't initially try to correct for it, because you're just going to end up in this weird cycle that will never work out. Skip it and trust that it'll sort itself out later. Now we find carbon monoxide. Where is it up here? It's on the wrong side. But is there the correct amount? One carbon monoxide here, one carbon monoxide here. It's just that it's on the wrong side. So what are we going to do? We're going to flip this reaction over. So we're going to make this, and do this with me in your notes, we're going to take this and we are going to flip it over. this is no longer our dude. Oh, wait, which? This, thank you. Yeah, that would have, yeah, thanks. Okay, there we go. Did you see what I did? I just wrote it down wrong. So all we did was flip this over. So we're here, and we're there. Yep. So we're like this now, right? But guys, when we flip this equation over, what else do we have to change? The sign of the energy value. So that is now positive. We okay? Now guys, this is usually a good time to go back and make sure you're okay. So carbon is on the right side and the right number. We agreed that we weren't going to worry about the oxygens and hope that that shakes out because they're in multiple places. And then guys, we've got carbon monoxide now on the correct side by manipulating this equation, and it also has the correct number. Once you've gone through that process, it is now time to add these up. So here's what you do. Bring down everything on the left-hand side. So we've got carbon plus oxygen plus So carbon plus oxygen plus CO2. So guys, I took this and this and this, and those are our reactants. We're adding up the steps. Hess's law. Now on the right, we've got CO2, we've got CO, and we've got 1/2 O2. So now I brought down the right side of all the different manipulated equations. Now guys, what we're going to do is we're going to cancel stuff out. So what cancels? We've got a carbon dioxide on both sides, so that cancels. Does the carbon cancel? No. Does the oxygen cancel? Half. So we've got a half here, and if we remove a half from the whole, that then leaves us with a half. And then, guys, we've got carbon monoxide, which doesn't cancel. Some of you are now seeing it. We now have carbon plus 1/2 O2 yields CO, which is this. Hold on a second. So guys, what we have done is by manipulating these, we have been able to convert these into a group of equations which adds up to our subject reaction in blue. So, and guys, follow the pen. The idea then goes like this, and I'll put it in a color that'll stand out. If these add up to this, which they do, then this is gone, then these add up to this. So now we need to do the math. So guys, and this is where signs are very important. So negative 393.5 plus 283, and I get negative 110.5 kilojoules per mole. And the original question said what? Of carbon. Now guys, there's one other thing that I'd like to show you before we start entertaining questions. You saw one of the two potential types of manipulation. What did we have to manipulate? We had to flip this over. Now guys, understand what I'm about to write down is not actually the way this question plays out, but let's talk about it. Guys, what if this equation balanced, what if this equation balanced with a 2 here? If the equation balanced with a 2 here, and if we were starting all over, what would we have to do to the equations that we're going to manipulate? Well, the carbon is still on the same side, right? It's on the correct side, but here we've got 2 carbons. Here we've got 1 carbon. So we would have to double all of this and then also double that. You got the idea? Those are the 2 kinds of manipulation that you will do. You will flip reactions over, and if you have to do that, what do you have to do to the number? Change its sign. Or you may have to multiply these equations by multipliers to make the number of atoms line up. And when you do that, you've got to also multiply the energies by those multipliers. That's the process of manipulation. Go ahead.
So you can't just multiply like one of those?
No, it has to be universal. And here's the thing. If you were to do that, and again, this really shouldn't be like this. If you were to do that, and if you were to just double this and not double everything else, you'd never get it to add up. You'd always find that when you start bringing things down, it wouldn't cancel properly. It would never quite add up. Good, just.
So why didn't we do that with the half?
Here?
Yeah, we had half of 2 up there. We didn't multiply.
Well, so if you want to take this back to the actual thing that we did, then understand that we didn't have to multiply anything by anything because we had 1 carbon and 1 carbon, and that was fine. And then we agreed we weren't going to mess around with the oxygens because they showed up in multiple places. And so, yeah, and so that's the idea, that if you've got something in your subject reaction that shows up in multiple places, you don't know which one to multiply. And you end up in this cyclic thing. It just gets nasty. So here's the bottom line. They will always give you equations that will work out. It's not like they're going to feed you equations that will never be manipulatable. So if you find a substance in multiple places, don't mess with it and trust that messing with other things will make these work themselves out. And then with the carbon monoxide, we had to flip it. So, yeah.
So if there's 2, and it doesn't fit, so if the C was from the same side.
Oh, I see what you're saying. Yeah, no. So by flipping one, you screwed up the other.
Yeah, so if there's 2 of the same, it'll always flip.
Well, or they could have just magically given you all the correct equations and they all just add up without any manipulation. But in the example that you were talking about, if you flipped one and that flipped the other one and it didn't work out, they didn't give you valid sample reactions. And they won't do that. So I've been ignoring. So go ahead.
It was me, but you already answered.
Are you sure?
Yeah.
Are we good?
It's just about how you're adding everything up. I was just going to ask about the energy, but you already.
Are we okay?
You're
Way ahead of you? Or
already doing the process.
a step behind you? Somewhere in there. So guys, are we comfortable with manipulation? Yeah. Yeah.
So I noticed early on that it could be very possibly, since I was using I was just thinking of the Boise
Yeah.
mythology, and I just thought, couldn't we just subtract negative 283.0 from negative 393.5, in essence adding 283.0. And so you went on this roundabout way, and I'm assuming that's because in chemistry you could just, in the real world, you could actually just do it that easily. Well, I suggested.
So, I mean, in this case, that might work, but you haven't discovered a universal problem-solving process. So I'd be careful about running down that road. It's certainly, this process is universal. That one specific way that this might have worked might work here, but you haven't discovered a universal approach. So, are we okay, guys? Okay. You're good? That's a mess. Isn't it interesting that you can make sense of that mess? Yeah, kind of cool. All right, so here we go. So we're going to get rid of that. And guys, we are now done with Hess's law by manipulation. So now we are going to transition into Hess's law by computation. And guys, Hess's law by computation involves what are called enthalpies of formation. So guys, let's talk about what on earth that means. So what is an enthalpy? What is enthalpy? Heat in the absence of work. What is formation? Guys, when you think of formation, given your background in chemistry, what comes to mind? Say it again, Caleb. Okay, so precipitating something, that's something that we've formed. Synthesis, molecules, but universally we're making things, right? So if you think about it this way, enthalpy is formation is the heat of making things. Makes sense, right? So it's actually Joey that brought us to the place where we needed to be. Specifically, when we talk about enthalpies of formation, we are talking about the change in energy that is involved in the reaction that forms 1 mole of a compound from its component elements, which is a synthesis reaction. So guys, fundamentally, and this isn't in your notes, but we can write it down, you take some X, you take some Y, you stick it together, you get XY. What's the delta H? That is a heat of formation, where X and Y are elements, XY is a compound, and the heat of formation then is the amount of energy needed to make XY by bonding X and Y together. You okay? Now guys, here's the part you're probably not going to like, but I just need to prime you for this because I'm the worst offender in the world. You will also hear these called heats of formation. Technically, that is incorrect because heat still allows for work. Enthalpy discredits work. So technically, these are enthalpies of formation and not heats of formation, but you're going to many times hear them called heats of formation. You're going to hear that out of my mouth too. And understand it's not two different things. Heats of formation and enthalpies of formation are the same thing, but it gets even worse because this is abbreviated delta H naught sub F. And now you're going, wait, doesn't H stand for heat? The answer is no, it stands for enthalpy. Yeah. But as we read through this rapidly, you see the H and heat just comes out of your mouth. It will for me. But guys, let's talk about what this means. I think you know some of this, but not all of it. What does delta mean? Change. H means enthalpy. What do you suppose the little F means? Formation. Now guys, what does the naught mean? And guys, this is not a degree symbol. This is the mathematical representation naught, K-N-O-T. In chemistry, it means at standard conditions, which in this setting is 20 degrees Celsius and 1 atmosphere of pressure. Doesn't matter. It's always going to be naught. It's always going to be at standard conditions. Oh, it's actually 25 degrees Celsius. But guys, this is the abbreviation for naught, for heats of formation, enthalpies of formation. And the naught stands for pure substances at 25 degrees Celsius and 1 atmosphere of pressure, but that is always going to be the case. So now guys, grab your books and open them up. Open them up to page 184. Okay, so guys, with the understanding that you now have that heats of formation, enthalpies of formation are representative of the amount of energy that is exchanged, given or taken in, as elements come together to form compounds. Guys, here's a table with a sampling of heats of formation. At the top of page 184. So guys, what do you notice? Anything jump out at you? Mostly negative, good. Which means what? Mostly exothermic. Now guys, why would that be true? So they're giving off energy, but why? So let's think about it. Here's X, watch my hands. Here's X, here's Y. These are elements. The compound is XY. So for X and Y to make XY, what do they have to do? Bond together. And guys, fundamentally, when bonds form, is energy given off or taken in? Given off. Guys, if you don't know this, you better write it down in really big letters. Anytime a bond forms, energy is given off. If you can't remember that, think about it the other way. Anytime a bond breaks, what has to happen? Energy has to go in. Think about it this way. In order to shatter a rock, what do you have to do? Hit it with a hammer. You've got to add energy to it. Guys, there's a universal principle that says to break something, you've got to add energy, and when something forms, energy is given away. You get the idea? Okay, so when we talk about heats of formation, we're talking about elements bonding together. When they bond together, energy is given off. Groovy? Not so groovy, though, because guys, look at benzene, look at ethylene, look at diamond, look at iodic acid. What are their heats of formation? Positive. So what's going on? What does that mean? Everything that we just established is false. No. What does it mean? Let's not try to explain it. Let's just talk about what it means. So what does it mean if you've got a positive delta H value? Energy is going in as the bonds are formed. And now you're thinking to yourself, wait a minute, as Everett said, everything we just talked about is false because we just said when bonds form, energy comes out. But now we're learning that for some of these, energy is going in as the bonds formed. Do you understand the tension there? So what's the explanation? Guys, the explanation is in chapter 19. We're not going to talk about it right now. We're not even going to explore it right now. The answer is in chapter 19, and I know that some of you would like to talk about hypotheses. Hold on. Some of you would like to talk about hypotheses, but we're not going to do it because we can't have a corporate intelligent conversation about it because we haven't talked as a group about entropy. When we bring chapter 19 into this, then we can go back and explain why. Not now. What you need to understand, guys, is that universally, this is still true. When bonds form, energy is given off. When bonds break, energy goes in. But there is something else at play here. It's called entropy. We'll deal with it in chapter 19. But we're not violating the underlying principle. But with that said, guys, what we are going to do is we're going to use this table. So you've got to understand, if you're still not comfortable, and I appreciate you're not comfortable because you're the kind of people that want to know, and you want to know right now, and I'm telling you, relax and wait. But guys, regardless of where your comfort level is with not understanding, functionally you've got to be able to use this table. So what does this table mean? Let's take an example that's not going to freak you out, like ammonia. You see it there? Let me explain to you what this is all saying. What this is saying is this. Ammonia is NH3. When ammonia is formed, 46.19 kilojoules is given off when that forms. Now, what does this form from? What are the elements that make up ammonia? Nitrogen and hydrogen. But guys, remember, nitrogen and hydrogen are both diatomic. So, to balance this, this needs a 1/2, and this needs, a 2/3. 2/3? 3/2. There you go. So guys, that's the bottom line. And you've got to be able to make this connection. When you look at this table, for example, for ammonia, and it says NH3 negative 46.19, that means 46.19 kilojoules of energy come out when half a mole of nitrogen and 3/2 of a mole of hydrogen bond together to make 1 mole of that. So every single one of these entries in that table represents the amount of energy that is lost or occasionally gained when these atoms bond together to form molecules. Are you comfortable with the idea? Okay, now, what's missing from that table? Well, there's obviously a lot, right? But guys, there's one glaring thing that's not there. The diatomics. And guys, you need to understand this. All of the diatomics are assumed to have heats of formation of 0. That is critical to what we're about to do. All of the diatomics are assumed to have heats of formation of 0. Okay. Do you guys now feel like you understand what heats of formation are? You're okay? Y'all caught up with me? Good? All right. So guys, here's what we're going to do. Don't write this down. We are now going to solve another problem. But it's going to be a manipulation problem. But I'm leading you somewhere. Do this with me. Write these down. Remember the previous problem that we did where we were given some reactions to manipulate? And by manipulating those reactions, we could come up with the energy of an overall reaction? Well, guys, we are going to do that again. But now, instead of having 2 reactions that we can manipulate, we're going to have 4 reactions that we're going to manipulate. And instead of putting the subject reaction below our manipulation reactions, I'm going to put them above our manipulation reactions. Nope. So, do you guys all have these written down? You're okay? You're good? Oh, tell you what, we're going to go on, but you can catch up. So guys, what's missing? If we're going to do a Hess's law problem, what's missing? The energies. Oh my gosh, we're missing the energies. Where could we possibly get the energies? In the table. Because guys, if you look at these, what are all of these reactions representing? The formation of 1 mole of each of these compounds. This is the formation of CH4O2, carbon dioxide, and water. These are all formation reactions. It's not a coincidence. So now let's go to the table and let's get the energies for these. And this is going to lead us to the magic tie between Hess's law by manipulation and Hess's law by computation through heats of formation. So guys, let's do this. So we need methane, CH4s, delta H, negative 74.8, negative 74.8 kilojoules. I'm being loose with significant digits and units. Oxygen. Oh my gosh, where's the heat of formation of oxygen? It's 0 because it's diatomic. That is 0 kilojoules per mole. Heat is neither given or taken in when the diatomics form. Now carbon dioxide, the heat of formation of carbon dioxide is negative 393.5 kilojoules. That's familiar. It was in the previous problem. And then guys, finally water. And why don't we agree that this is going to be water in its gas phase. Negative 241.8. Okay. All right. Are we okay? All right. Now, guys, and all that we've done is we're replaying a manipulation process. We're now ready to manipulate. But in order to manipulate, what do we need? A subject reaction. Here it is. Feel free to write it down. This is our subject reaction. This is the combustion of methane to form carbon dioxide and water. Okay. So guys, we're going to do this together. You should be able to do this on your own, but let's do it together. Remember how the process works. Start on the left and work to the right. The first thing we find is CH4. Do we find it in our subject reactions? Yes. But what's the problem? It's on the wrong side. So what do? We rewrite this. CH4 yields C and 2H2. This is now no longer our reaction. But when we do that, what do we have to do? Change the sign of the energy associated with the process. Are we good on that one? Now let's do the next one. The next thing we run into is O2. What are we going to do? Nothing, because it shows up in a lot of different places. Is that okay? Or does it? Yeah, it does. So there's 102 on the... Oh, but you know what, guys? Actually, no. In this case, we do need to focus on it because it is a primary product in this. So this one we are actually going to have to flip around. So we're going to go O2, flip this over. Yeah, and change the sign of the 0, right? Flip this over into O plus O, and it doesn't change the number. Okay, now guys, we've got carbon dioxide. Is it on the right side? Yep. And we've got water. Is it on the right side? But is there the right number of them? No, so we've got to go 2 and 1 and 2, and then functionally we double this and we'll make it negative 480. Thereabouts, yeah. Oh gosh, thank you. 2 and 2 and 2, and that doesn't change. Good call. Okay. So now, guys, yep.
So since we have two O2s on the same side, then does that mean that we still have to double?
I'm not sure if I know what you mean.
No, because we're doubling. So on the left-hand side, we've got in two separate equations, you got O2s.
Right.
So why are we still doubling?
Well, and so this is where it's a little bit of a stretch because I'm trying to make this fit a connecting process. And so in order for this to work, we've got to function under the assumption that this O2 is this O2. And if this O2 is this O2, then we have to flip it and double it. Just trust me for now. It'll shake out. You'll see why. Okay, so now guys, what do? We add everything up. So here we go. We've got a CH4. We've got 2 O2s. We've got a carbon. We've got another O2. We've got, where are we at here? 2 hydrogens and another O2. Did I do that right? CH4, 2 O2s, a carbon, another O2, 2 H2s, and an O2. Yep. Are we good there? Okay, then guys, on the other side, we've got, where did we go? We've got a C and 2 H2s, and we've got an O and an O. What's that? Oh, you're right. 2 O's and 2 O's. And then we've got, wait a minute, something weird's going on here. A C, hold on. What is this doing? A CO2 and 2 H2Os. I don't think this is going to cancel right. It does? So the CH4 stays. How does it cancel right? So let me switch colors. This isn't going to cancel correctly. These are gone. The carbon is gone. So we have 4 O2s over here. Oh, yeah. So we can go like this, and those are gone. There we go. And so we've got CH4 plus 2 O2s yields CO2 plus 2 H2Os. You okay? Okay. How we doing? So guys, here's what we've then verified. And then you're going to have the aha moment. What we have now verified is that by manipulating these, we were able to get them to sum in order to come up with our subject reaction. Is that okay? Now guys, watch. We're not done with the problem, right? How do we then figure out the delta H for the reaction? What do we have to do? Add all of these up. But now guys, watch really carefully. This is the critical bit in all of this that we just did. Look at what we did. Did you notice, guys, that these two reactions right here were both connected to our reactants? The CH4, and the O2. And these two reactions right here were connected to our products, the CO2 and the H2O. Do you see what I'm saying? Now guys, look at how we treated them differently. What did we have to do to both of our reactions that were connected to the reactants? We had to flip them over. Why? Listen carefully. Why did we have to flip them over? And here's the answer. What are these reactions? They are formation reactions. But guys, reactants are not formed. What happens to reactants? They are consumed, which is the opposite of being formed. So what we had to do is we had to flip both of our reactant reactions over, because reactants are not formed, they're consumed. So we flip them over in order to account for that. Does that make sense? But what did that mean we had to do to these numbers? Change their sign. Now guys, what about the product reactions? Did we have to flip those over? Why not? Because they're products. They are in fact produced. But guys, what else did we have to do to this reaction and this reaction? Doubled them. Why? We had to multiply by the coefficients. So guys, let me distill this for you. Here's what we did. Listen close. We got these numbers, which are the heats of formation for these substances, CH4, O2, CO2, and H2O. We got the heats of formation for all the components of the reaction. Then what did we do? We changed the sign for the heats of reaction for the reactants. And why did we have to change the sign of these? Because they're not actually being produced, they're being consumed, which made us a reaction, so we changed the sign. That we had to multiply by the coefficients so that we can keep track of the fact that we needed two oxygens and water. So bottom line is this. We got the formation, we changed the sign on the reactants, we multiplied by the coefficients and added them all up. Would you agree with that? Guys, that entire process is summarized in this equation. Go through this again with me in your head. We looked up the heats of formation. We changed the signs for the reactants. We multiplied by the coefficients, and we added them all up. Because you don't need to write those down, but I'm going to. We got the heats of formation. We changed, I'm going to write out changed. We changed the signs for the reactants. We multiplied by the coefficients, and then we added them all up. Guys, all of that is contained in this equation, which is also on your cheat sheet, on your AP equation sheet. Don't look for it yet. Watch this. So guys, where in this is look up the heats of formation. Right here. Get the heat of formation for the the products. Get the heats of formation for the reactants. Then guys, where is change the sign of the reactants? The negative. Subtracting something is functionally the same as changing its sign and then adding it, right? Right. Where is the multiply by the coefficients? Those are the ends. And then where is the add it all up? The sigmas. So guys, this equation is just this mess. Change the signs for the reactants, multiply by the coefficients, and add them all up. That is this. Get the heats of formation, change the signs for the reactants, that's the subtraction, multiply by the coefficients, and then add it all up. That's what that equation is telling you. So guys, find it on your equation sheet. Did you find it? Now guys, notice there's a huge omission, isn't there? Not emission, omission. What's missing? The n. They assume that you know to multiply by the coefficients. I mean, you're welcome to write it in on here if you want, but it won't be on the one that's on the AP test in May, so I wouldn't. But you'll lose this anyway, so. But guys, that's the bottom line. So what are we going to do in homework? Well, you're actually going to have the opportunity to solve both of these types. You'll be solving some through manipulation. You'll be solving some of them using this equation. Understand, guys, it's different sides of the same process. Here's the thing you're going to hate. You're going to hate this for the rest of the year. Many times they will not give you the heats of formation, and they will expect you to look them up in an appendix in the back of the book. Let's go find that appendix. I can never initially find it. So guys, this appendix is on 1060. It's appendix C, right? Yeah. So guys, on 1059, there is appendix C, and it's got the numbers that you need. They will ask you to look them up. You won't be asked to look them up on the AP test. So some of you are going to get smart about this and realize that I already looked them up because they're in the answers. So you're going to get smart and you're going to go, rather than look them up in Appendix C, why don't I just pull them out of the solutions that are posted online? That's fine, but the problem is that as you're looking for the numbers, you're also going to see the problem-solving process, right? You can't see one without the other. The hazard is if you look at my answers to get the values, you're then going to actually rob yourself of the experience of solving the problem. So be careful about that. So guys, here's your homework. Yeah, so your homework is this, but in addition to that, we are now going to summarize chapter 19. So, the way that this is going to work, guys, is because you have an abbreviated homework assignment tonight, it's not unreasonable, especially given the weekend, to say also summarize chapter 19. We're going to do the same 4-quadrant system. And guys, we will turn all of this in then on Monday. In addition to that, guys,